All right. Doing a div 3. We're already. Whoa. Oh, my screen isn't visible. Yeah, I'm just doing a div 3 for fun, because why not? Here we go. It's already started 5 minutes ago. But yeah, let's go. Actually, should I whip my tablet out? There are n players playing a game of the circular table. They take turns eating the food, and any player can go first. During that turn, if player eyes dish remaining, they must eat exactly one dish. Then the next player starts their turn, and continue until all dishes are finished. Determine the number of players that can possibly be winners. Wait, what? Oh, depending on when you start. Any player can go first. Okay. Yeah, that makes sense. It's just the number of maximums. Because if you just start with the value directly after it, but also if you're max -1, no, then you can't win. Then you just can't win. How do I close this? We've got a game on an A by n on an array of n. If it's non-decreasing, the game ends. Otherwise, you can remove it from the array, an element from the array. Determine the minimum possible number of elements that can be remaining in the array after the game ends. The minimum possible number. So actually, if we've got let me bring up a tablet here. The minimum possible array. That's interesting. So if we've got some kind of array, then I have to end up with an increasing sequence. But I can't keep deleting stuff once it's increasing. So I've got to find one, 2. Okay. Yeah. I'm struggling to share this with you guys, but what the hell? What's the shortcut for Windows plus arrow keys? I've just got a window that's stuck. Oh, sure. Yeah, I can't believe I forgot that shortcut, actually. Okay. But yeah, this problem's pretty simple. I'm just trying to get this thing to share. There we go. Okay, here it is. So yeah, I'll just submit this one and start explaining from the next one, honestly. So basically, we have an array. And if it's non-decreasing, obviously we can't remove anything because that's when the game ends. So then it's the whole array. Otherwise, we can only take a pair that's like a drop, a pair that's a drop, and just remove everything else. And come down to those two values, and then remove one of those two as well. So otherwise, so in that case, it'll be 1. Um, where did the remarkable go? Okay, here we go. So next problem. Oh, I've got to read the next problem first. Ideally, I have to see the problem to solve it. I think that's how it works. You've got a string of length n. Initially, it contains only lowercase Latin letters. In one turn, you could choose any pair of integers that are the same, and everything in between is a star. And you set the endpoints to a star. So, can you do that? So this one you cannot. So the first letter has to be does not have to be equal to the last letter. So this is just DP on ranges, right? What's M? 5,000. Yeah, this is just DP on ranges. This is similar to, this is similar to many problems. But what happens here? We get M and a string. Why does this not work? Yeah, I don't know what's wrong with this. Anyway, I set can LR to be true if I can solve Li and IR. Why does or equal not work? Is that not a thing? Bitwise or assignment operator. Yeah. What do you mean? I've been using this since I was born. It works on booleans, buddy. Vector reference? What do you mean? Bro, not one of these. What's wrong? I don't. L and R are integers. This is fine. This is not fine. I'm actually intrigued. What's up here? Wait, seriously? What? You can't do that? I'm just curious at this point. Like, what? What? Why not? Okay, so apparently you can't do this. It's just a syntax thing, or if it's a vector of booleans, you can't do that. Which is stupid, because that's syntactic sugar for this, right? I don't get why you shouldn't be able to do this. It's just syntactically, but yeah, it's fine. I guess bool just doesn't work like that. What did I do to the problems? Did I close the problems? I think I closed the problems. Okay, we're kind of slow rolling through this contest just because I'm investigating some random issues. the niceties of C++ syntax and what you're allowed to write. Okay. Portal. You're given a permutation P of length n. There are also two portals located at positions x and y. The portal position I is initially located between the ith and I plus first elements of the array. If I is 0, then it's located before the first element, and if it's n after the last cell. Before mine, what? So you push a value through a portal. So like you push a 3 through this, and it appears on the other side of this one. Or you can push a 2 through this and get 3, 2. Oh, you get 3, circle 4, 2, circle 1. Okay. Or the other way around. Find the smallest permutation you can obtain. The portals are deleted at the end. Okay, so... So how does this work? So I've got some kind of... I'm starting with like 3... portal, 2, 4, portal. I'll just do zeros for the portals, honestly. Portal 1. And so what kinds of permutations can I get here? So this portal basically, like this block, somehow the block between the two portals, I can just cyclically shift as much as I want because putting 2 here pops it out here. So this is like a cyclically shiftable block. But then while I'm cyclically shifting it, then these guys also just remain. So yeah, this block in the middle can never mix with the block outside. So if you look, it's always just 2, 4, and then 1 and 3 can be combined, and 2 and 4 can be combined. But it's also always 3 before 1, right? 3 can never go after 1. So if you look at the two portals, anything between them can just be cyclically shifted as much as you want. And then anything on either side, this stuff, all I can do is just reshape it. So is just like choose where I'm splitting it. So the key thing here is I have to choose the split point for this stuff and the cyclic shift for this stuff. So the first thing you need to do is choose the best cyclic shift for this. and then I choose the best position for the other one. And what? Oh, right. Since this is a permutation, it makes things kind of easier. So, yeah. Because if this was an arbitrary string, I'd have to do like suffix array or something. But since it's a permutation, it makes choosing things like the best cyclic shift easier because you just choose the smallest value. And x and y. Okay. And x and y. And the second line of each test contains, I'm just going to move this. The second line of each test contains an integers permutation of length and node. Yeah, it's just okay. P. Now I have to move it into two different groups, right? I just print the smallest permutation. So I could have even just already split this up into cycle. I don't even need P. I need cycle, and then I need to put like cycle and segment, basically, and I have to choose a split point in the segment. If it's greater than or equal to x but less than y, then it's in the cycle. Otherwise, it's in the segment. So now I just do cycle 2, which I'm going to start with the smallest element in the cycle. Vectors don't have vectors have subsegments. So maybe I should have done it this way around. Yeah. So now I've got this cycle that's ready. And then since I want like directly minimal, I just need to have final permutation. I just go through everything in the every value in the segment, and then if I haven't done the cycle yet, and b is greater than cycle 2, the first value in cycle 2, if b is bigger than the first value in cycle 2, then I want to do the cycle next, right? Hallelujah. What? Okay. 4043142. So this is the example we had. And I just had 1, 2, 3, right? I just had 1, 2, 3. So it should be 1, 4 in the middle. Wait. 404. 404. Oh, this is the whole range. I just had 1, 2, 3. What happened to the 4, man? It's print cycle 2. It's just 1, 2, 3. How is it 1, 2, 3? What happened to 3, 1, 4? Oh man. Okay, so the first one's correct. Now the second one is just 2, and I'm just doing 2. What happened to segment? Oh, I'm never pushing it. Okay. Oh, what? TLE 5? I TLE'd for problem C. N squared should be fine for problem C. But I TLE'd. Why did I TLE? Oh, wait, what am I doing? What am I doing? What am I doing? This is, yeah, TLE, man. Uh, what's that? I just bashed out a DP that was too slow. Why did I do that? So for a specific range, I just need to check all the possible split points. And see if that works. is quadratic term. But that's cubic term. Is there a greedy here? There can't be a greedy, right? I don't think there can be a greedy here. Can this ever fail? Yes. No, but then you can just do this. Like this. This would fail though. Let's say these weren't meant to be paired together. That means they're both going somewhere. That means one of them like ends up here and one of them ends up here with stuff in between as well. If you've got stuff in between like this, and this is possible, that means this once this pair is all full of stars, before this pair becomes full of stars, you fill this. So this part is like solvable separately, basically. This part is separately solvable, which means you could just pair this up and pair this up and solve this part separately. So actually, this greedy just works. If you have two letters next to each other, if you just take the first two letters, if you just scan through, but what if none of them are next to each other? Something has to be next to each other, otherwise it's impossible, right? So if you don't have anything next to each other, like this, then you can't start with anything. And so something has to be next to each other, and then you just do the greedy of like first pair. So we go through the string, and we delete the pair once we see it. Wait, is this a linear time solution? If implemented correctly? Because we have some string, and then we just go through the string. Anytime we see a pair that's equal, we cut them out. And then we just check if the next pair is equal. It's like n log n. Yeah, no, this is wrong. Oh, we don't even need the log. We can just do linear with a q. Oh, wait, I need to know which positions are still left inside, right? So I guess I need a set anyway. I might as well just have this as a pad for explicit equality. All right. So now Yeah, okay. I've also got to erase. LLM. Let's see. Just remove this, right? And then this, and then this. Equal begin, equal erase, equal begin. What? Am I not doing tests correctly? Now it says yes. Oh, I didn't give it the number of tests. I mean the length of the string. 0, 1, 3, 4, and then it just doesn't pair up the last two. So I lower bound I. At this point, I should no longer be in positions, and neither should J. I lower bound I. I take its previous one. Oh no, not that. If S at this index equals S at this index. Index value confusion mistake. That looks correct now. All right, that is correct now. Alice and Bob playing a game on an array containing n integers with Alice going first, and positive integers. On each player's turn, if A is non-decreasing, the game immediately ends. Otherwise, the player can choose an element x from the array and positive integers y, z less than x, such that x equals y, z, and replace x with y and z in any order. If no such move is possible, the game ends. If A is non-decreasing, the game also immediately ends. Once the game ends, if A is non-decreasing, then Bob wins. Otherwise, Alice wins. Oh, okay. Who will win? So Bob is trying to make the array non-decreasing at any point, and Alice is trying to stop that. So Alice goes first. So if the array is non-decreasing, then it'll just be correct. If the array is, then it's just over and Bob wins immediately. If the array is initially not non-decreasing, then Alice is going to start. And if there's no move possible, she just wins. If there is a move possible, she has to make it. This is kind of ambiguous, actually. It should say must here, or can. I think can here is ambiguous. So you can choose a number and factor it. So Bob wins this because this number doesn't have any factors that are bigger than this. So you put them in any order. Right, but for this number, what order you put them in is going to. So for this number, wait, Alice wins here because she just puts them in the correct order. Wait, what? Bob wins. Wait, what? No, Alice just wins here because. She's got to choose 2, 3 on 6. And so she'll do 3, 2. But why is this Bob? Oh, this is already undecreasing. Okay, fine. So if you can choose a value, assuming the game isn't immediately over, if you can choose a value that's that you can make decreasing if you're Alice, then you're happy. Especially if, like, let's say you have a composite number like this that's just the product of two primes, two different primes, then you just win. Like, if the game isn't over and there's a number that is the multiple of two primes, you just win. Also, especially if the game, if you've got, say, like 7 times 11 times 13 times 17 squared or something, then you just choose you just choose the smaller one here. And you just do like this and this. So if you have anything that has more than one different prime inside, or like is, if it's a prime number, then you can't do anything to it. If it's a prime number squared, then the only thing you can do is, as Alice, is split it, and that's kind of annoying for you because it still stays non-decreasing. But if it's anything else, you can split it by taking the smallest prime out and putting on the right, and then putting the rest on the left. And you can actually never make this. As Bob, you can never make the. Oh no, you can. So if it's a power of a prime, then that's not as good for Alice. But if there is something that has at least 2 different primes in its factorization, and the game isn't immediately over, then Alice can just win the game by splitting it like this. Like, take the smallest prime out to the right. And then whatever Bob does, this thing will always be bigger than the thing to its right. So Alice can win in that case. So if the game isn't immediately over, then if there is a number like this, then Alice just wins. And otherwise, if there is no number like this, what does that mean? That means everything is that means the game isn't over immediately, and there's everything is either a prime or a prime to a certain power. And in that case, if everything is prime or prime to a certain power, I think the game is deterministic. Like, while things can be split, they will be. And splitting, and hear me out, if I think it doesn't matter how you split these, in the sense that if Bob could ever win, i.e. if Bob could ever make this non-decreasing, then it will also be non-decreasing if he doesn't lock in, basically. If he doesn't constrain and he just plays, at the end, if it was possible for him to make it non-decreasing, then it will be non-decreasing by just at the end anyway. because like if it was non-decreasing at some point because of like certain moves he played with powers of primes, then if he just lets these moves play out, it'll still be non-decreasing. So, oh wait, no, it won't. It won't. It won't, because maybe he doesn't want these to drop below some other values before them, right? So that he could have like 37 here, and so he has to play the right moves to avoid these dropping. But so maybe Alice can just avoid this. If this is not non-decreasing now, that means there is a drop somewhere, right? There is a drop somewhere. So for this to be possible to win for Bob, the thing on the left has to be composite. So it has to be a prime to a power. Like this. And the thing on the left, so it's just a race of like Alice decreasing this and Bob decreasing this, kind of. Maybe Alice just always wins these. Like, I feel like Alice wins most of these, basically. I need to find the cases where Bob wins, and then Alice wins the rest in these, like, prime cases. So, Bob definitely wins if, like, this kind of. If you just expand all these primes into just, like, 777, 7777, because if the game doesn't end with Bob winning, then it just keeps going, right? And if it keeps going, it'll get to this. So if this is a state that Bob wins, then obviously Bob wins. But otherwise, if this isn't a state that Bob wins, so like if you split every prime up into its factorization and just write it into itself many times and just write it out. If Bob doesn't win that, so let's say we have like a 7 to the 3 and then a 2 to the 3 afterwards. So basically, if these primes aren't in sorted order, then what happens? So this is 7 cubed, this is 2 cubed. I feel like Alice wins most of these. And why? Because Alice goes first. Alice does not want these to be non-decreasing. And Alice knows that if you flatten everything out, there is some drop somewhere, right? So if you flatten everything out, there's like a drop from 7 to 2 here, for example. There is a drop from 7 to 2. So Alice can just try and make that drop happen as fast as possible. Wait, no, maybe not actually. So if this was already 7, imagine this is already 7. So new test case. This is already 7. This is like 2 to the 10. And then there is a 3 squared and a 3 here. Wait, a 3 to the, let's just say 3 to the 20 and 3 to the 10 here. So this is currently increasing, and then there's a drop at the end. So this is not currently game over. But if Bob drops this to 2, 3 to the 10s, it will be game over. And I don't know if Alice can stop that. Can Alice stop that? I mean, Alice can drop this, right? But what if this was like some huge prime around 3 to the 10 instead, then... wait, I haven't checked how big these numbers are, by the way. Up to 10 to the 6, okay. So if this was some huge prime up to 3 to the 10, then Alice cannot drop this. Cannot decrease this. So Bob making this move is just game. What can Alice do? Alice can drop... Oh, but Alice can just take this prime out, right? Yeah, this is what we said. So if it's Alice's move and it isn't game over and it's just a bunch of primes, then if the primes are decreasing at some point in the final like spread, so if we ignore the powers, if there's a drop in primes, then Alice can take this 2 out and just never lose, because we know that like even if this was like this prime is just bigger than the 2, so whatever power this prime is in, like even if you drop it to the first power, it's still going to be bigger than 2. So the final solution, what does this look like? If the game is over, it's over. If the game is already over, then it's over. Which means either like you can't make no moves. So if it's non-decreasing, then Bob wins. If it's already non-decreasing, if there are no moves left, then Alice wins. If there are moves left, then we check if there is a number with like a multi-prime number with a number with more than one prime factor, then Alice just wins. Otherwise, you check if the final, if the prime bases are sorted, then Bob will inevitably win, and otherwise, if they're not sorted, then Alice wins. Because of this technique. Bro, what the hell? What is this problem? I hope there isn't just like a one-liner that solves this, but it feels like you kind of need to do this. Okay, we're gonna be churning out some code here. Let's do it. So these numbers are up to 10 to the 6. So first, I'm just going to write a quick prime factorizer sieve of Eratosthenes. Although I won't call it that. I will call it the max value is 10 to the 6, and then prime factor of smallest prime factor of min prime factor of these numbers. I'll just compute that. I'll pre-compute this. So if the, oh man. Okay, so I've pre-computed that. Now I need to prime factorize all the numbers in the, well, Okay, we've got factorization code now. Now I need to turn on this lamp because you guys can't see my face. Now I need to do something else. That doesn't really help. Now I need to do something else. Now I need to solve the problem. So if it's, let's remind ourselves of the plan. So if it's non-decreasing, then Bob wins. So if it's already non-decreasing, I kind of want to have this. Okay, I'm just going to see how Bob wins. No, otherwise you have to check if they're all prime. If the min prime factor of AI is not AI, so it's not prime and not 1, so that there is a move on it, then there is a move. If wait, I need to factorize all these. So if no moves, if it not is moved, then Alice wins. If otherwise, if is multi-prime, then also Alice wins. So actually I can just do that. So now we've got these, we've done these 3. And now I need to check Bob only wins if the prime bases are sorted. Got a notification that some statements slightly changed. that notification actually induced PTSD because I'm now used to CF Blitz Cup, and that is exactly the way you get notified when your opponent solves the problem before you, which means they get all the points and you get none of them. So it's kind of PTSD inducing. Prime base is sorted as false. Yeah, now I just need to check well, whether basically when you expand everything that it's sorted, which means I just have to check if this, like, I is less than I plus 1 in terms of the expansion. So if factors I empty, if AI equals 1 continue, if AI plus 1 equals 1, and AI doesn't equal 1, therefore, since we're still here, then prime basis sorted equals false. And otherwise, if AI equals and break, and otherwise neither of them are 1, so they both must have prime factors, and they both must only have one prime factor, because otherwise we would have done his multi-prime. So it's just, we just check the value if factors I 0, wait, factors I 0 second, first, as in the prime base, is greater than factors I plus 1, 0 first, then also same thing. So actually I'm going to move this into here. So if the prime base is oscillative now, I see out Bob. Otherwise, I see out Alice. I print Alice. Okay, we made a mistake on this one. We say Alice when it's Bob. This one, right? Why do we say Alice? Let me just number these. 1, 2, 3, 4. We missed one. Oh, they're out. Okay. Alice 4. Okay. Really? All of them are Alice 4 and Bob 1. So this is Bob 1 because it's already, wait. Non-decreasing. It's not non-decreasing. Oh, the last one. This one's non-decreasing. Yeah, Bob 1. Next, so apparently all these cases have moves and none of them have multi-primes. Which is, this is just wrong. Like this one and this one, both like 6, 6. What are we doing? This should be Alice 2. These should both be Alice 2, at least. I don't know what's up here, but so this is wrong. Is my factorization greater than or equal to 2, buddy? Greater than or equal to 2. We've got some kind of error going. What? Did it crash? I think it crashed. Let's see. Wait, what? Yeah, let's see what's going on here in more depth. What? Oh, because I'm doing return 0, whereas I have test cases, which is rather stupid of me. I should be doing continue for all these. Alice 2, okay. Now here, what's the prime factorization of these numbers? 6 and 7 prime factorization. It's a prime number, 68192 prime factorization. It's a power of 2. It's a mega power of 2. Okay, so in this case, it should be Bob winning because it should be Bob 3. This is Bob 3. This is classic Bob 3. It's the 13. This. Okay, so this is, I mean, this is correct. But so two is not bigger than 677. What? Oh, come on, man. Come on. Sloppy. You're just being sloppy. You're just being sloppy. All right. Let me just dump that there. Divisive battle. Okay. Yeah, we're chilling. All right, that worked. Very fast judging time. Why couldn't we have this in Blitz Cup? I was instantly judged. Nuclear reactor 2. Bessie needs to produce energy as possible in her nuclear reactor. She has n different. What are we on? Yusuko? She has n different particles. Each particle is defined by two integers x and y. The particle generates x units of energy but has a reactivity y, meaning that it can only exist together with at most y other particles in the reactor. Formally, if this particle is chosen to generate energy, then at most y particles other than itself can also be chosen to generate energy. Bessie must choose a subset of particles that satisfy this constraint to generate energy. The amount of energy that she generates is equal to the sum of energies of the particles in the subset. There is a shop with m particles. Bessie can buy exactly one particle from the shop. For each one, determine the maximum energy that Bessie would be able to produce if she were to buy only that particle from the shop. Bessie is not required to use the particle that she purchased. So I've got n and m, and the descriptions of the n particles and the descriptions of the m particles. And so basically, we have a bunch of queries, m queries of how would the answer change if we added this particle to the question. So I mean, obviously, first we have to just consider the problem without the additional particles. So imagine we've got some particles chosen. So x is the amount of energy we get. Is it the total energy, right? The sum of energies. So x is the amount of energy we get, and y is the number of particles we're happy with. So this is good if it's high. This is good if it's high as well. So let's say we've sorted the particles by y, right? We've sorted the particles by y. So we've got like 2, 3, 3, 3, 7, 5, 5, 6, 6, 6, 8, 9. This is telling you how many other particles can be in it. So if you choose this guy, then you're capped to at most 3. I mean, it doesn't have to be this range, but you're capped to at most 3 particles. So this is the expensive one. So basically, what we're doing is we draw a line. And this line is saying like, okay, this is how, draw a line, do we draw a line? We choose how many particles we're going to choose, let's say some k, and then that excludes some prefix, because these are like pretty picky particles, they want to be chosen alone. And so we have to choose k from the remaining, at most k from the remaining suffix. It's fine if we choose less. But the trade-off here is that a bigger k is better because you choose more particles, but a smaller k might be better if you get access to some of the more juicy ones on this side. So that's the problem. I don't even know if I know how to solve this without the queries, to be honest. So if we put these in coordinate space, this is y, this is x. Actually, that's really annoying. I'd rather put x on the other side, but just nobody does that. Just the fact that it's called x, I guess, means I'll just put it here. No, can't do it. Got to do this. So, no, actually, it doesn't. Yeah, it doesn't matter. Let's just do this. So x is on this axis, on the x-axis, and x is telling us what the value of the thing is, and the y is telling us how lenient it is in terms of how. So, like this is just much better than this, for example. But the tough part is if most of the points are situated on this kind of direction. Okay, so what are we doing here? We want to know what is the largest number we can pick. So the trick here is, if we were just solving it for one problem, we just have a line that was slowly moving down. We're slowly increasing the number of values that are available to us. And as the line moves down, because suddenly we're saying like, okay, we're going to choose fewer values. We would unlock these values down here, and so each time this metaphorical line passes, this imaginary line passes a certain point, we would look at that point and say, from now on, we're allowed to use this point. So let's just compare it to our current list of points that we're using. obviously, as we move the line down, we also have to pop the point with the worst x out because we don't have space for it anymore. And then we push this point in if it's better than any of the current points in, and if it's better than the worst point currently in, and then we pop that one out. So we would use like a priority queue to store all the points that we've got, and we would pop and push. Yeah, that's how we would implement it, but we have queries. Of how would the answer change if we had this extra particle? How does the answer change with one extra particle? Specifically just one. So obviously the answer either remains the same or changes only if there's a better solution involving that particle. So if there's a solution involving this particle, so let's say we've got a new particle in town, you know, we got a new boy in town, like this guy. If there is a better solution, the new solution will be at least as good as the old one, and we only have to check whether there's a better one involving this guy. So when's there a better one involving this guy? It's if this guy. So this guy sets us already a bar for y. Like the line has to be below this because we have to be allowed to use this guy. So in other words, you know, the number of particles we choose has to be at most y of the new particle. And then, but with that constraint, you might still want to not choose this many and choose fewer so that you can unlock more of these nice ones further down. So what's the trick here? The trick here is we have to pre-compute. So for each possible number of particles that we'd be choosing, so for each possible value of k, let's say k is 1, 2, 3, 4, 5, and so on, we have to pre-compute the best score. This is what we're already doing with that sweep line. So that's not really much pre-computation, we're just finding the best score. So whatever that was, this is like one number. And then best score with one gap, i.e., what's the best score if you want to choose k values, but let's only choose k minus 1 values. But all the others have to those k minus 1 have to have y at least k. So as in they have to be open to admitting one more value. Okay, and then when y new comes in, we'll already have the best one chosen out of these. So just best here, and then y new gives us a cap for k, and then we go up to that cap in that prefix. We should have prefix maxes calculated on this, and so we take this prefix max and then plus x, and then we just compare to this best over here, and that should do it. Okay, that should be it. That should be it. All right, now let's lock in, because I'm kind of hoping we can get. I was kind of hoping we'd get a bit further through these problems. There are a lot of them, and they're quite cool problems actually. Okay, so solving problem F. So what have we got? We've got test cases, and then all the points we have, and then all the extra query points. I don't know if I want to call this M, actually. I'm going to call this Q just because I want to. And we're dealing with the queries online, so we're not pre-computing anything specifically for each query. We're just pre-computing stuff generally and then dealing with each query as it comes. So now how do I need to store these points? I need to store them by sorting them. Yeah, I'm just going to store them as pairs. I'm going to call that A. What order do I want them in? I want them in order of Y. So it's going to be YX. Oh, so YX, A, C and X, and then Y. How big are these values, by the way? They're kind of chunky. They're quite chunky. Okay. All right. Now I'm going to sort them by Y in reverse order, so that I'm starting with like the values at the top of this diagram and moving down. Okay. So now I've got to pre-compute everything. So what am I pre-computing? Best score for a given K. Wait, K can be up to N, right? Like, as in, yeah, K can obviously be up to N. So I'll just call this score. Best score with this K. Score with gap. Again with this K. 1 plus N. So K is okay, so we're going to start. So we're going to start with K equals N. This allows all points to be chosen in theory, but some of them will be restricted because they won't want us to choose them. So, all right. Actually, I think I can just do this straight with a for. So I loop through the case, and now I've got a priority queue. Wait, is priority queue default max or min? It's max, so I need to switch it to min. Priority queue, the values in it will just be, they need to be tagged with their x values so they can be sorted. Priority queue of xi, and I'm popping the one with the smallest x. So this is just okay. current score equals 0. These should be long. So I go through all possible k's, and then so we've just had a new k introduced. So I've also got a pointer to next point equals 0. So while wait a minute, so k just decreased. Okay, so I'm going to have a add point. Wait, I'm just going to add the point here. I don't know why I need add point. So I'm going to add the point. While next point is less than n, and a next point first, which is the y coordinate. Actually, I'm just going to plus y here, just so y is like the total k. And that's how I was working with it in the first place. So while the y that it allows is at least k, so while the y hasn't gone down that by too much, I'm gonna add this point. PQ in place, a next point second with next point. So how much value it gives me and its index. Current score plus equals a next point second and plus next point. Okay, so I've added all the new points. Now I've got to remove all the points, as many points as I need to cut it down to k. So while this PQ size is at least bigger than k, I need to drop some values. So top of the priority queue, PQ pop, and current score minus equals current x. Okay, so now I should have at most k values. And now I'm going to say score k equals current score. And score with gap k equals current score as well. But if PQ size is exactly k, then score with gap k minus equals, we're going to take off PQ top first. We're just going to subtract the worst value. Okay, so this should be ready now. Just one more step of preparation. Score with gap prefix sum. It's the longest variable name I'm going to use. Score with gap prefix sum k equals score with gap prefix sum k minus 1 plus score with gap k. Okay, I think we're ready for the queries now. Yada yada, how do the queries work? They'll be the same. So I'll get an x and a y. Wait. Best exists. So the number I choose has to be at most yq. But of course, if that's bigger than n, then I can just choose at most n. So that's max k. And then I need to do score with gap prefix sum, prefix max. And prefix max of this. I need to whip out the max with k, with max with most this k. And I need to add xq to that. Something like that. Okay, 67, 169, 778. Oh, these are meant to be on the same line, which is why it's complaining. Which is not why it's complaining. I'm just going to do it like they want anyway, but we have a mistake somewhere. It's this 8 that I'm printing. So let me take a look. Why do we have test and queries? That's a bit odd. I'll be honest with you. Okay, so the energy in the reactivity, where is the test? I've got 1 and 2 queries, so 617081. Am I no longer sharing? What is this? What is happening? Okay, so the issue with this is, what is the issue with this? Let's see. I've got a point at 6, 1. So x is 6, y is 1. 7081 are the queries. So the first one, and I've rewritten these y values of 2, 1, 2. So if I'm choosing the first one, the answer is just 7, and the second one, the answer should be 14 because I can choose both. And how should that be reflected in my data structures? So, yeah, that's the thing. That's the thing. I haven't accounted for the fact here that I might actually be willing to take at most n plus 1 points. Because I can take all n of the original ones and the extra one. So I've just assumed that I'll take like at most n points. But actually, I could be taking n plus 1 points in the final answer. So where am I using n here? Okay, k equals n. I'll just start with n plus 1 here. Well, next point is less. So basically every use of the variable n, I just have to check. So this use is fine because it's just an index. This user's not fine, this user's not fine. This user's not fine. So if I just do something kind of risky here and just rename n with this. Wait, okay, I'm not going to do that, but so I'll catch some of the n's. Yeah, it seems like I've changed most of them. Okay, now let's pass that test. That makes sense. I've gotten used to submitting very, very easily because of that Blitz Cup competition. I used to be very careful with my submissions, so I'm gonna take one more look through them before I submit. Yeah, these are integers. Okay, those were the obvious mistakes. Yeah, of course, this sample isn't particularly strong, so we're gonna have to see how it does on the actual tests. Okay. We've got half an hour left, slightly under. We have an integer x and a list of n operations. Each operation is a string starting with one of the symbols. We have an integer x and a list of n operations. Each operation is starting a string starting with one of the symbols, plus, minus, times, or divide, followed immediately by a positive integer y. Yeah. We'll randomly permute the operations, then apply all of them sequentially to x in the permuted order. Help this dude compute, help AK's lol coding, compute the expected value of x. What? The expected value? That's kind of cool. You can do that. Formally, we have, yeah. Yeah, okay. We have a bunch of operations. The sum of n squared over all test cases does not exceed 3,000 squared. What? Why are they saying that? Why are they saying it that way? N squared doesn't exceed 3,000 squared. Okay, so basically an n squared solution is fine, is what they're trying to say. So we're taking a uniformly random permutation, right? Yeah. So main thing basically is we have a bunch of multiplications and a bunch of additions. And our final value is a bunch of, so it'll be, I mean, we can think of just everything as a multiplication or addition. And we've got either a negative number or a positive number or, you know, or a fraction. So we've got either times v or plus v, where v is in Q. These are all our operations. And so how do we, what do we start with? An integer x. So we start with x. So we're starting with x. If it was just times or just plus, obviously the order doesn't matter. So we can kind of split this x with the plus v's. The x is like x plus 3 minus 5 plus 2 plus 7, let's say, right? And then we can split these up conceptually and just say like the final answer will be some random variable big X, which will be the sum of like x0, which is in a sense like the contribution to the final answer of X. So X multiplied by some coefficients, which will actually just x0. We know what that'll be. Actually, it'll just be the product of all the multiplicative coefficients times X, and then X1. Let's say if we just number these addition operations. So in this case, in the sample, like +1, +4, +5, +6, -7, -8, if we just number them 1, 2, 3, 4, 5, 6, then x1 plus x2, and these random variables are how much this addition contributes to the final answer. So if this addition ends up coming up, if one of these additions, let's say the +7, happens after all the multiplication operations, then it'll just be +7. But if it happens before, then it won't. Then it'll be something else, like something modified. So we can think of it this way, and we can actually, the expected value of this sum, because of the linearity of expectation, is the sum of the expected values. You can prove this. The sum of the expected values. So somebody's calling me. The expected value of the sum is the sum of the expected values. So the issue with this is, wait, I'm not streaming this live, am I? Just checking. In case like people are calling me to let me know that I'm accidentally. Yeah, no, this is private. Nobody can see this. Okay. So the sum of the expected values, the expected value of the sum is the sum of the expected values. So for each one, I just need to find out the expected value of the contribution. And so for each of these constants, I need to find out what the expected contribution is. And for each one, now we've got the contribution of each one is the expected value of a product, though. It's the expected value. It's the initial coefficient. It's the initial addition value. So we'll call that AI times the expected multiplicative contribution to this additive value from each j. If I just create this notation, but it's now a product, and this is annoying because the same rule that I did up here doesn't hold for products. Where, by the way, these y's can only have two values. The y is either equal to 1 if the multiplication happened before I added this constant, so it didn't affect this constant, or it's equal to y ij either equals 1, or if what I just said, or just the multiplicative, just this value that I'm multiplying by, Cj. Otherwise. So my question is, how do I find this expected value? Because the expected value of a product. But the nice thing about this is the expected value of this product is the same for every additive coefficient. So so by the way, so we know x0, and we know that every AI is multiplied by the same thing. So we just need to find this. We just need to find this, which is basically if you randomize the order of all the multiplications, and then what? If you randomize all the multiplications, and then take a random prefix of them, i.e. like you insert yourself into a random position, including potentially the start, so that's the empty prefix, or the end, which is the full prefix, corresponds to the full prefix. Then you're taking the product of the random prefix. And what is the expected value of that? So I've got a bunch of numbers that I'm multiplying by. Let's say like 1/3, 2, 4, 6, 3. I'll just do them in increasing order because why not? Random permutation of these, and then I multiply by their random prefix. And I want the expected value. So I mean, for each of these values, it is 50-50 whether I end up multiplying by it. For each of these values, it is 50-50 whether I end up multiplying by it. Which means okay, let's say there's just two of them, A and B. We want to see what the expected value is of multiplying by A and B if both multiplications are random. So if they're 2 and 3, for example, the expected, like we want the expected value of A times B, where big A and big B are all either like 1 or little a, 1 or little b. So, and it's 50-50 for each one. But they are correlated, right? Because if you actually write out the permutations, if we've got like A, B, B, A, A, B, B, A, A, B, B, A. So here we're multiplying by AB, AB, 1, 1, B, A, right? So it's actually 1/3 chance of getting 1, 1/3 chance of getting AB, and 1/6 chance of getting each of A and B, which is not what is like, you can't just 50-50 this. Wait, I wonder if that was some kind of what if we fix how many are the permutation? Like how big the prefix is? In that case, we want the expected product of k random values out of n. If we fix the prefix, then we're taking like the probability of this size prefix out of the brackets, basically. And so now it's just expected product of k in n. Wait, is the stream still running? Okay, so how do I find the product in this case? If I take a look at the number of so does this fixing prefix actually help? So I know how big the prefix is that I'm going to take, and for each. No, it's just the expected product. When can I ever do expected products? When is expected products a thing that I can do? Expected products, when independent, right? Expected products are the product of the expected values. So I need this to be independent. This still isn't independent though. Because now that I have a fixed length, choosing one value means a different value is less likely to be chosen instead of more likely to be chosen. It used to be up here that choosing one value means you're more likely to have lots of values after you. So like this. So it's more likely you'll have chosen another value. Now that we fixed the prefix size, it's less likely. So how do I make things independent? It's tricky. The stream's still running. Okay, so So yeah, by the way, what I just said about the independence is like the expected value of the this thing is the covariance of x and y. This is the covariance. And this is 0 if, and when x and y are independent, this is 0, and that exactly means that like this expectation is equal to the expectation. So basically, if I make these variables independent somehow, then the expected product is nice and easy. So how do I turn, let me reset. So I've got a bunch of coefficients, multiplicative coefficients, and I need to find their expected products when you permute them and then place a divider at a random position between them and choose like the right half. So whether or not a value is chosen there, they're not independent variables. Can I somehow make them independent? If I fixed the length, I tried fixing the length, but that doesn't work. Because if you know the length, then choosing one makes the choice of another less likely, actually, instead of more likely. How do I make these independent? I need to express this product some other way. Could also simulate it. That sounds really dumb, actually. I shouldn't simulate it. Oh, no, yeah, I can't simulate it because I need the exact value. Yeah, I need the exact value. Nice try, dude. Yeah, I can't just Monte Carlo this. Can't just Monte Carlo this. So, how do I make these independent? So, I've got the product of these, but only product of some of them. So, how could I have expressed these just for 3 values? What could I have done? I could have said 1, 1, B, A, B, B, A, B. If I know oh, wait, can I do DP on this? The expected product of first K given of K of the first M is of some K of the first M. Yeah, I think this is the way to go. I don't think I'll have time to do this, but I think that's how you do it actually. Yeah, I've got 4 minutes. Yeah, I'm not implementing this in time, but this is how you do it. You bring in yeah, like it took me the whole time just to bash out this boilerplate code. Honestly, this is like not the solution has not begun. Uh, yeah. All right. I mean, I'll keep coding maybe. I should probably know how to do this. This is interesting. I mean, it's like it's out of competition anyway, right? So it doesn't change much. Um, Standings wise, probably not great. I can't even see myself. Yeah, it doesn't really matter. Jesus. What? Yeah, I guess I kind of get solving this quickly, but just okay, sure. Um, so how do I? I'm pretty sure this multiplication can just be expressed. Wait, does expected value in multiplication work modulo something? I don't know how expected modulo multiplication works. I'm pretty sure it works normally. Um, and I'm also like I'm looking for the expected value modulo m and not the expected value modulo m. So I think the other way it wouldn't work, but this way it does. I'm pretty sure that's how it works. So I think I can just store these divisions directly as multiplications modulo. But then how do you do this? So you need to do a dynamic programming style approach of the expected product of some k of the first m um, in these multiplicative coefficients. And so if you've got the answers and you're moving to a k of this m, how do you do that transition? So you know the answers to k minus 1 of n minus 1, k of n minus 1. And it'll be the sum of these with multiplied by some coefficients. And the coefficients, what will the coefficients be? The coefficients are the expected like the conditional the coefficients of the conditional probability of, I mean, depending on which coefficient it is, taking or not taking one more, given that we already have like k minus 1 or k already out of m minus 1. That's basically just, what is that? If you have we can model this as already just like an existing permutation where we're inserting points one by one. So if we've had m minus 1 already, we've had k minus 1 of m minus 1, what does that mean? That means we've got us being like that, like the addition operation. And then we've got some C's. We've got like C, a bunch of C's after, like some C with some coefficients, and some C's before as well. And the number of C's after is k minus 1, because those are the ones we took. And the ones before are the rest. So we now have, like, there are in total m plus 1 here, because there are m C's and 1 A. And for the next, there are m minus 1 C's and 1 A. So there are m dots here. So there are m plus 1 spaces between dots. And the probability that next C is after AI is, this is k minus 1, 1, 2, 3, k minus 1, and then this one as well. So k in m plus 1. So this coefficient is actually k in m plus 1. And the probability that next is after AI given like k minus 1 so far. Next C is before AI given we already have k. This is the other option. So we already have k to our right. And again, we have m in total. But now we want to end up on the left. And now it's how many slots? There are m plus 1 slots in total, and k plus 1 of them don't work. So m minus k slots are good. So m minus k in k plus 1 slots. And so these are the conditional probabilities. They're actually quite simple. And so we do k this times like the dp, like the expected coefficient, this dp, which is the expected coefficient, choosing k from m, is this times dp k minus 1 from m minus 1 plus m minus k over k plus 1 times dp k m minus 1. This is like the formula. That's the maths. That's how that works. And so I'm pretty sure division, as an implementation detail, I'm pretty sure division modulo works correctly. But, you know, if it doesn't, then this is going to be wrong. So I don't know maths, but I don't know all the maths here. But I'm pretty sure this will just work the way I do it. If I just treat the coefficients, if I just treat divisions as multiplications immediately. If that doesn't work, I'll look into it. Yeah, how do I, let me just, so instead of this, I'm now doing if C equals multiply, then mult push back V, else mult push back inverse of V, 1 over V. Okay, So now we've got the coefficients ready. Wait, what if it has no inverse? It might have no inverse, because the value... Oh, but by a positive integer. Okay, thank you. So all the values have an inverse. I appreciate that. They don't give us zeros. I don't think zeros would be much of a problem. They would just be annoying to deal with. Oh wait, what? Yeah, no, I'm stupid. We wouldn't need to invert zeros because nobody's dividing by zero. That's dumb. And multiplying by zero is fine. We don't need to invert that. So yeah, there are no problems. We have no problems. So what are we doing next? We're setting up this DP. So this... How does... All right, doesn't work. I was trying to get this to stay on top. Anyway, so what am I going to do to this now? I'm going to set up the DP this according to this equation, basically. And what do I initialize that with? Doesn't really matter what order I write these. This is the number chosen. And so, I guess it could be 0. So I have to do dp km equals, I'll just write this as division for now, times dp k minus 1 m minus 1 plus m minus k over k plus 1 times dp k m minus 1. Okay, so now the issues here, except for this division, are... So if m minus 1 is 0, that's an issue, actually. So if m is 1, that's the only one. Oh, it's m plus 1. Wait, something in this equation is wrong. First of all, I copied it over wrong. But also, these should both be m plus 1. So m plus 1, m plus 1. Okay, now it's fine. Now the issue is this. Yeah, this is the issue. So k minus 1 here. So m minus 1 is fine, but k minus 1. So if k is 0, then this should be 0. What does that mean? If k is 0, that means we haven't chosen anything so far. So Is this probability wrong? We said this was... Oh, k is how many we've got here. Oh, these are only the cases where we choose it. Wait, what have I done? These are only the cases where I choose it, but we also do the cases where we don't choose it. Wait, no, that's these cases. Yeah, what am I talking about? Okay, so this is the case where we don't choose it. And so if k is 0, what does that mean? The probability of that... The expected product of all these... Ah. We got a Bayesian mistake in the mix. So what does dp represent? dp represents the probability, the expected product of some k of the first m. So if I chose k values in the first m values, what their expected product would be, right? And I'm doing that case-wise, and so this is the case where I'm including this, where this value is included, and this is the case where this value is not included. So expected product, we've got as the expected product given include times probability of include plus the expected product given exclude times probability of exclude. And so what have I done? This is what it should be. So I don't think I've included these terms properly. So this term, the expected product given, I'm including it. What is that? That is the product of the current values, which is like this product here is, wait, yeah, this value is the expected. We can take like product prime, which is the product of the rest, times, and then given that we're including it, this is a constant. So times like 2 or something, times whatever value this is, Cj. But we have to multiply it by the probability of including it, not by the probability of stepping to this point from the previous state. And the probability of including is, from this state's perspective, just in general, is just it being one of the k. So it's k in m, right? Oh wait, but it's not uniform. Oh, but given I know that I'm choosing k, then it is uniform. It's k in m times the expected. So k in m of the time, it's just this value times the expected product of the rest, times the product of the rest. So this. in that case. And then I also need m minus k in m. So if I choose the rest, as in if I don't choose it, because the probability of choosing this guy is k and m, because I'm choosing k out of m values. So yeah, these were the wrong types of probabilities here. So that's wrong. In fact, what it needs to be is dpkm equals k over m times, again, I'll fix this later, times the coefficient. I'll just call these m and a. Wait, no, I've already got a c. I'll leave it. Times cj, where j is m, minus 1. That's the coefficient. Times dp k minus 1 m minus k minus 1 and m minus 1 plus m minus k over m times 1 times dp k minus 1 minus dp k m minus 1. And so here, if k is 0, just as a sanity check where we failed on the previous one, here if k is 0, this is 0, and this is just 1 times the previous one. So that makes sense. Yeah, so now we need to deal with that explicitly though, because this being 0 will crash. So if k is bigger than 0, dpkm equals add dpkm mult k by inverse of m. Oh, I've overloaded mult. Okay. All right, I'll just change everything then. I'll change all these. Apply all except for this. Oh, I've got add as well. This is A. Yeah, apply all, except not this either. Okay, so I add I just need more lines for this. I need to multiply that by dm minus 1 and by dpk minus 1 minus 1. M minus k by the inverse of m, multiply that by dpk minus 1. That this is C. So that's what we're doing, basically, instead of this. dp00 equals 1. We're multiplying by 1 initially. And then, so at the end, we will have a probability, we will have not a probability distribution, we'll have, given each length, we'll have a value for that length. And now for each length, we also need the probability that we end up with that length. So the probability of choosing k out of n, because we're uniformly choosing a point in a permutation to put a dot in, we're uniformly choosing a split point in a permutation, it's just 1 in. Uniformly choosing split point in permutation, so probability of choosing of having k values to the right is 1 in plus 1. So expected coefficient I should really be multiplying by this at the end. I wanted to do it in between just to make it explicit, but I don't need to at this point. I think it's explicit enough. That tests for this? Oh, there are. Okay. Redeclaration of n. That's not great. Oh, yeah, I mean, okay. I'm just going to call that in. I'm sorry. I've used it too many times. Whoa, big negative number. Why? This is never negative. Is anything here ever negative? Oh, the values can be negative. This minus v. Base minus v. Whoa, wait, I swear that worked before I switched this to a minus. Did it work? What? Wait. So I've got code that works on all the tests, but not at the same time. Okay. That's weird. Let me just check that everything is like modularized correctly. That I'm not just adding stuff, or I mean, I'm subtracting this, but this should be fine. Oh, wait. No, it shouldn't be fine. What am I doing? This should be at most m. So that was actually ending up negative sometimes, this thing. I don't know if that affects things. Apparently not, but I mean, this is correct. This is more correct. Okay, let's break down one of these examples that it's. Oh, wait, I was looking at the wrong sample. It's not this, it's this. So times 2 minus 10. Okay, sure. So we start with 10, we've got a minus 10 and a times 2. The expected result here should either be 10. I mean, the result is either 10 if it's this way around or 0 if it's the other way around. So the expected result is 5. So what would my calculations say? My calculations would say that the 10 will contribute 20 and the minus 10, it's 50-50 whether it's minus 20 or minus 10. And so the expected value there should be minus 15. So what is the coefficient that we get here? Oh, come on, man. The answer is bigger than the base. Look at it. The answer is bigger than the base. Okay. Yeah, that seems legit now. No more random. Okay. So which one was the? Why did I leave this in here? This was the wrong one. This was the wrong one. So this is what we're doing. Yeah, I kind of want to run this now. I assume I would be able to, because the contest is like finished and stuff. Submit. Oh, I can submit. Oh, because Div 3s don't have system testing. It's brilliant. It's lovely. Very nice. They have open hacking. Accepted. Let's go. Okay. Well, I mean, I don't think I would have been close to getting that. It's because like, even if I didn't explain it, there were just a bunch of bugs and stuff, but yeah, fairly nice problems, I'd say. 6, 7. Am I doing 6, 7 right now? I'm kind of hungry. um, I'm rather hungry, but yeah, I'm up to that. I'm not up to that. There's kind of a fun set of problems. Kind of did them quite slowly, but I guess that's what happens when you're out of practice and you need to explain things as well. Let's take a look at this. What is that notation? It's kind of strange notation, my friend. Positive integers I and j, define fi of j as the maximum integer k such that I to the k divides j. Define fi j as the maximum integer, the highest power of I that divides j. Okay, a number j is considered special if f6 of j is bigger than f7 of j. So 6 divides j more times than 7 does. So 6 is special, but 67, which is divisible by neither 6 nor 7, and 7, which is divisible by 7 but not 6, are not special. You're given an array A of positive integers. In one operation, you must increase every element in the array by 1. Your task is to find the minimum number of operations needed to make all elements special at the same time. This is the strangest, oddly specific problem I've ever seen. I can't really imagine a scenario where somebody would need this, but, I'm sure someone would cook one up. Like some kind of cryptographic... Okay, what's happening here? Okay, so that's the problem. We need to find the number of times we need to increase each value, the whole array. So it feels like it would be hard to construct a case that you have to increase too many times, because I think it's quite rare for a number to... Oh no, it's not actually that rare for a number to be special. I mean, sorry, it's... I was going to say most numbers are special, but they're not, because this is a greater than sign, not a greater than or equal to sign. So, like the number has to be divisible by 6, right? So we print -1 if there is a number that is not divisible. If they aren't all the same mod 6, because all the numbers need to be the same. All need to be the same mod 6, otherwise it's -1. So if they are all the same mod 6, then I feel like it'll always be possible, just because if you just keep cycling enough multiples of 6, I feel like you should get there. I feel like you should get to a case where like the numbers aren't divisible by 7 eventually. So let's try and construct this and figure out what's wrong with it. So these aren't the same mod 6. The rest, this one we have to increase by 7 to make it special, because increasing it by 1 would also make it divisible by 6, but but increasing by 1 would also make it divisible by 6, but it would also be divisible by 7, evidently. These we need to increase by 12, because 42 is already divisible by 7. We need to increase it basically twice. Like, we only consider multiples of 6, essentially. We need to initially shift everything so it's a multiple of 6, and then just keep shifting. I think the trick here... No, never mind. The fact that it's 6 and 7 specifically is a bit weird. I mean, maybe it's just 6, 7, but they're also, like, the fact that they're adjacent numbers, is that a coincidence or not? So, could I make none of the values divisible by 7? Or could it still be impossible? Okay. Depending on what I'm adding, yeah, the final value I had, mod 42, if I'm adding k mod 42 has to be so I know what k mod 6 has to be, and depending on what k mod 42 ends up being in the end, given that I know what k mod 6 is, there are 7 options for that, and for each of those options, a different subset of my list of numbers ends up being divisible by 7. So actually, numbers don't, like, they obviously don't stop being divisible by 7 as you increase them. And if you just keep adding, you won't get to you won't generate a state where none of them are divisible by 7. So if you group them by these mod 7 groups, or mod 42, into these 7 groups, so if you group them mod 7, basically, if you group the numbers mod 7, 4, 5, 6, 7, if you group the numbers mod 7, then if you can find a group that's empty, that's great, because we can cycle to that group being the group divisible by 7, but that group's empty, so none of the groups will be divisible by 7, and none of the values will be divisible by 7, and they will be divisible by 6. If no groups are empty, that means we always have at least one divisible by 7. That means we now need to choose which one we're dividing, which group to focus on. And for that group, okay, so we have always at least one divisible by 7, right? So again, k mod 6 is fixed. Now, if we have this kind of case, now let's fix k mod 7. This means the other 6 groups are fine as long as, we obey this k-mod 6, because in the other 6 groups, they'll all be divisible by 6, because everything's going to be divisible by 6, but they won't be divisible by 7. But this bad group remains. Need to make it divisible by I think this will be a binary search problem, by the way. Need to make it divisible by 6 squared, at least, in terms of what powers of 6 it's divisible by. So the next number has to be divisible by a higher. This group has to be divisible by a higher power of 6. Okay. So I know k-mod 6 and k-mod 7. So now we get like a subproblem. So numbers should be the same mod 6 squared. Now I know k mod 6 squared, and we group group the numbers based on their modulo. What? The value modulo 7. Oh, you can't see anything I'm writing. We group the values based on their modulo 7 squared because now that we're making these values divisible by 6 squared, they'll be fine as long as they're not also divisible by 7 squared. So the power of 6 should be greater than the power of 7. So a group based on mod 7 squared. And we basically repeat the same thing here. So if there is at least one empty group, we're fine. If there isn't, we're not fine, and we're in a mess. So we just keep going. And so we've got this situation where we start off with k mod 6 being fixed, and then k mod 6 is fixed. And then we try different values of k mod 7. This might either just work straight away, in which case we've got a good one, or if all the groups are kind of, wait. So if the values mod 7 are, if we've got like 117, 2, 3, 5, 6, if we've got one of each, let's say we don't have a mod 7, right? And this means we need to up it to a certain value. This could still be fine, right? We could still up it to this value. What power do I need to go up to here? I'm feeling that something is amiss in this solution. This might be a slow solution if I have to implement it correctly. I mean, this isn't a solution yet, obviously, but the route I'm taking down this problem. Yeah, came on 6, came on 7. I still need to check everything. So let's look at how big this problem is. All the values are up to 10 to the 9, which means the highest power of 6 we could have is log 6 of 10 to the 9. What? Log 6 of 10 to the 9, which is up to 11. So we could have up to 6 to the 11 already. Up to 6 to the 11 already. And because of the number of values we have, which is 2 times 10 to the 5, each time we split this, so I'm just trying to get an upper bound on how much we might have to increase by. If it's possible, what's the highest answer we might have to output, basically. So 6 to the 11 is as in 11 is like log 6 10 to the 9, write it down. So if you imagine each number being split, so we start with one group, like what's a worst case bound on what the answer would be? If you imagine all numbers, we fix modulo 6, what the answer is. Let me just go through the process again. So we fixed what the answer is, modulo 6. Came on 7 now. We can always, the optimal answer won't always be choosing the smallest group out of these ones for Kmod 7, but won't always be choosing, that won't always be the optimal answer, but I can use it as a bound. So if I choose the smallest group out of these, like choose the smallest group, there'll be n over 7 values left in this group at most. At most n over 7 values, and now I have a specific value of Kmod 36 given by these values. So, and I keep going until I have, if there were, so I have Kmod 36 given by these values. And the answer I get here is then they're grouped based on mod 7 squared as well. So mod 7 squared, so if there's an empty, So in here if there was an empty group, then I just had an answer for any k that is this modulo 6 and this modulo 7. Would just work. So this any k like this works. So I had a mod 42 answer, so therefore the maximum I had to add was 42. In this case, now if I've gone down this branch, I've got k mod 36, I group mod 7 squared. If I've got an empty group, then I know what k mod 36 is, and I know I don't know what k mod 6 squared times 7 squared is. But now, if I don't have an empty group, again, I can choose. Otherwise, choose smallest again. So now I've got at most n over 7 times 7 squared values. And then this will give me, again, if got. Wait, now I have to group by. Wait, now I've got k mod 6 cubed group by k mod 7 cubed. I've got an empty group. Yada, yada. So I think just the fact that I'm dividing by into these groups sequentially. Wait, no, it doesn't work. Wait, what have I done? Because I can't just choose a mod 7 squared here, can I? If I've already forced myself to be in this group, in this chosen group. Because if I chose a group, I committed to a modulo 7. So grouping by mod 7 squared, actually, yeah, this only splits me into 7 extra groups, not 7 squared groups. So 7 groups. This is 7 groups. And this is again 7 groups. So this isn't 7 times 7 squared, this is n over 7 squared. So yeah, it makes sense. All right, so if I group in, if I do k mod 6 to the L times 7 to the L, then this splits into n over 7 to the L minus 1. So if n is less than 7, then I can choose a value mod 42 that just works. So basically, since n is at most 6 to the 11, What's log 7? Wait, really? Oh, okay. That was so it's not 6 to 11. This is the value. So 7 to the 6. So if that's at most 7 to the 6, then I'll have an answer. Guaranteed answer was 6 to the 6 times 7 to the 6. So like 6 steps down this rung. And that's basically like just over n, just under n squared, right? This is like 1, 2, 3, 4, 5, 6, 7, 8, 9. So the answer is less than 10 to the 10 is the conclusion here, because that's what I'll be adding to, like at most 5 times. So I'll be adding less than 6. It was like 5 times 10 to the 9 or something. So less than 6 times 10 to the 9. Two values that are at most 10 to the 9. So all values stay under 10 to the 10. All values are going to stay under 10 to the 10. That doesn't really help. But this number of steps that I'm taking, yeah, I actually don't know how to solve this problem yet. This is quite confusing. It usually takes me some time to like think through, get used to this kind of problem. So yeah, I guess I'm just gonna leave it there. Honestly, I'm quite hungry. But oh wait, let me look at this tutorial for the other problems at least. Rate the contest. Rate the difficulty. I thought those problems were actually really good. Let me go back through them first. Eating game. Come on. Oh, this was just like the maximum number. The number of different maximums. Maxima in the array. Sure. Yeah. Deletion sort. What's the minimum number of elements you can leave? Yeah, this was like either 2 or whatever. We can delete all elements besides these 2. And delete AI to get 1 remaining. So the answer is 1. So these were observation based, but they were really simple. This problem was, I feel like, a step up. Like it wasn't very hard, but it was like a step up, a big step up from these two. Like these two are like one-liners. This one was like you had to think. So yeah, the observation for this was that greedy works. What if you delete characters instead of replacing them? Instead of replacing characters with stars, just delete from the string. Then the operation becomes deleting 2 adjacent characters that are equal. Yes, it does. Wait. Yeah, that's true. I didn't look at it that way, actually. I did this pretty badly. We go through the array n over 2 times, removing a pair of equal elements whenever we find one. This problem can also be solved in ON using a stack. Oh, and of course I missed the quadratic solutions pass. See, this is the problem with me. I just, this wasn't that slow to implement, but like I didn't need to do that. Oh, I think I actually realized, and I just wanted to do it anyway. Okay, fine, never mind. Yeah. All right. So the key thing here is that looking at the problem with as deletions, basically, like it never harms you to do any deletion. Apparently, I only showed that it never harms you to delete the first pair. But I guess if you have two adjacent letters, then if you were going to delete the two of them with different characters somewhere else, yeah, you can. Yeah, makes sense. You can show that. Okay. So yeah, I think this is a good problem. A was like an average problem. B was a good problem. C was a good problem. D. Why do they have two code snippets? Well, probably for different complexities. They've done it with a stack. Yeah, basically it's just like I messed up C. I messed up C big time. Okay, D was the portal one. This was cool. I mean, it wasn't that interesting when you start thinking about it, but yeah, I like it as a problem. They're going to change the order of the elements, but they can change the positions. Yeah. Yeah. Divisive battle. I was playing a game. Oh yeah, this was a strange problem. I've never seen such weird, like, so many different cases arise naturally. So yeah. Whoa. Making a small prime number appear in the array after a number with a large prime factor. Yes, that ensures that Alice wins. That is the key play for Alice. Making a small prime number appear after a number with a larger prime factor. Oh, that's true. With any larger prime factor. It doesn't have to be, yeah, okay. If Alice can win, she can ensure victory on her first move. Yeah, that's what I got in the end. But that's not really something you guess, right? That's like something you realize after you go through some of the cases. If A is non-decreasing, Bob wins immediately. Otherwise, if there exists an element that is divisible by two distinct primes, then she can ensure her victory by replacing it with XO, P, and P. Yes. Since this is a multiple of Q, there will always be a multiple of Q that appears before P and is greater than P. If no such element exists, all elements are either 1 or prime powers with form this. Define an array B such that... Oh, actually, yeah, I think this... C, D, where is D? This check here was... Wait. Oh, this is E. This was redundant because you'll get through to this anyway. If this didn't catch you and this did, then neither of these will catch you, so you'll get through to this anyway. Define array B such that BI is 1 if AI is 1 and is the unique prime factor otherwise. If BI is non-increasing, then Bob will win. Otherwise, there exists an I such that that, and then Alice can win. Yeah, okay. How do they implement this? Prime base. Got a set. Oh, they just need the set of primes and not the powers. So I don't actually end up using the powers. Yeah, that's right. If is sorted, if min element. Oh, they've got this quite cleanly implemented, actually, quite nicely. Nuclear reactor. Wait, let me rate this problem. Device fast. Yeah, I thought it was good. Nuclear reactor. Yeah, got some particles. That stuff. This was not that hard. But it was quite nice. Yeah, for notation, by the way, I just incremented all y's by 1, so this constraint became y is greater than or equal to k. Just FYI. Yeah, okay, these hints are kind of obvious. Process k in decreasing order. Yes, this is like the first key thing you do. If Betsy has to use a sharp particle, which of her particles should she replace it with? The one with the smallest x? Yeah, obviously. Yeah, I mean, these are obvious, but you need to go through them. We can iterate on the number of energy particles from n to 1. We can only use particles greater than or equal to k minus 1. Store a set or max heap of the k largest x values. As k decreases, we add particles. Moving the smallest, yeah, we did this. The answer A will be the max of SR. We can run the algorithm again, but use maximum sets of k minus 1, reserving an extra slot for the sharp particle. We can store the sum s for each k prefix max. Yeah, this is exactly what I did. Okay. And that code seems to be a lot shorter than mine once again. Skill issue? Question mark? Oh, it's not a lot shorter than mine. Never mind. Not yet. I'm chilling. Okay, I actually like this problem a lot. I mean, you know, it was like, it was cool. What was this? Yeah, of course. Fix the permutation. For each plus y, how much would the answer change if it was removed? Yeah, this is the contribution point. How can you calculate the expected value of the product operation to come after all the plus y's? Replace this. Consider the contribution of each plus y to the final answer. Its contribution is equal to the product of the y and the expected value of the product of x operation to come after it. So yeah, we just need that. For each k, we need to compute the expected value of the sum of a random subset of k. Of the product of random subset. Product, buddy. To do this, we can use a dp, where dpij is the sum of the products of all subsets. They've done this slightly differently in terms of the actual implementation, but the idea is still the same, I think. Oh, yeah, I actually recalculated this. I didn't realize it was dpmm. I just recalculated it. This looks more complicated than what I did, honestly. But I mean, I had more complicated transformations. But yeah, it seems like they've done kind of the same thing. I will go through this afterwards, and I will go through this afterwards and work out what they've done in a bit more detail. But it looks like more or less they've done the same thing I did. I think this was a good problem. But yeah, I'm now gonna go have some food because I'm super hungry. Okay, yeah. That was the stream. See you guys.